This is mass-to-mass stoichiometry.
Before we begin, we're going to start with some definitions and background knowledge you'll need. First, we're going to start with AMU, or atomic mass unit. It is the weight of a single atom, but one cannot measure something this small. So instead, we use molar mass. It is found on the periodic table. You guys might have all seen this before. Looks like this. It is right below the name, normally. And this comes from Avogadro's number, which is 6.022 times 10 to the 23rd particles or atoms in 1 mole. When you take the molar mass, if you don't have just one element and it's a compound, you add up each element to form that molar mass. Before starting, make sure the reaction is balanced. In our case, all of the reactions will already be balanced. Getting to this one, this is a form of stoichiometry, which is a form of math studying the ratio between products and reactants in chemical reactions. The most important part of this is to show your units. This is very important and you will get lost if you don't do this. Molar mass is always in grams, so if you're given a different unit like milligrams, you will have to convert. For example, there's 1,000 milligrams in 1 gram.
Before we get started, we want to ask a couple key questions. First question is, what is a mole and how does it apply? A mole is a unit of measurement used to count the number of particles in a substance. It is the foundation of chemistry, and it simplifies the conversion of the mass of elements by establishing a common ground. Next question, why is this topic important? This allows chemists to figure out the amount of a reactant or material that is available, or also the amount of product needed for a reaction to occur. When is this used? Mass-to-mass stoichiometry is used in pharmaceuticals. Pharmacists use this to find the exact amount of reactants needed to produce the wanted reaction of the medicine they are creating. Lastly, how can you solve for the mass of one substance when given the mass of another substance?
To begin this problem, we need to figure out how much mass of carbon is needed to fully combine with 10 grams of oxygen to make CO2. So let's first look at what we're given. We are given 10 grams of oxygen. And so this is what we have to start with. So we see that oxygen is O2, and this is because, as you know, oxygen is diatomic. So when you have a diatomic, that changes the process a little bit, which is why I'll be showing with carbon and oxygen. So when you start with the 10 grams of O2, make sure you add your units. You then have to use the conversion factor, which is the molar mass over 1 mole. This equals 1, so it works out in the equation. So since grams is here, it's now going to be in the bottom of the next one, and you're going to figure out the molar mass of O2. If you take the periodic table, which is right here, oxygen's number is right there, and you see that it's 16, but since it's diatomic, the molar mass is 32. So 32 grams of O2 over 1 mole. And then we take this thing we like to call the molar ratio. It's basically 1 mole of the substance, it's the coefficient of the number you're taking, and the coefficient of the element you're trying to find, and you multiply them together. So since we have 1 mole of O2 here, we need to put the O2 on the bottom, so we have 1 mole of O2 for every 1 mole of carbon. They're equal. And now we are trying to find mass. So now we have moles, we need to go back to mass, so we're going to use this conversion factor again, except the units are going to be switched because we need to go to grams. So we're going to put moles on the bottom. So we're going to have 1 mole of carbon, and then we're going to go back to our molar mass, which I explained earlier. And carbon is right here, and it says 12.01. So we're going to have 12.01 grams of carbon. And then you're going to multiply them all together. And you're going to end with an answer about 3.75 grams of carbon. And as you see here, the units cancel out. So you go from what's on top here, and then it goes to the bottom. So it's kind of like a diagonal. So these grams cancel out of O2, and then the moles of O2 cancel out the moles of O2, then the carbon cancels out the carbon, and then you're left with grams.
Okay, for a second practice problem, we have, if you start with 5.5 grams of sodium fluoride, how many grams of magnesium fluoride will be produced? We're given a balanced equation as well. Pause the video now and try it, and then play the video, and we'll review it. To begin our math, we start with what we're given. We are given 5.5 grams of NaF. Now, we need to convert that into moles. To do so, we find the molar mass. 41.99 grams of NaF is equal to 1 mole of NaF. Now, to convert to magnesium fluoride, we need to find the mole ratio. Due to the balanced equation having a coefficient of 2 next to NaF, we need to have that in our math. For the 2 moles of NaF is equal to 1 mole of magnesium fluoride. Now, since we're in magnesium fluoride, we need to convert into grams. To do so, 62.31 grams of magnesium fluoride is equal to 1 mole of magnesium fluoride. Note that as we go along, the units cancel out. Moles of NaF, moles of NaF, moles of magnesium fluoride, and we end with grams of magnesium fluoride, which is what we want, as said in the problem. Our final answer will be 4.08 grams of magnesium fluoride.
Thank you for watching our video on mass-to-mass stoichiometry.
For more practice problems, there will be homework problems linked with answers to the video.